Hey folks, this is my summary video to go along with our assignment 10, which is about annuities and sinking funds. We're not going to talk too much about the sinking funds idea, but annuities is, well, they're the same thing, only in a slightly different guise. All right, so first a little bit of history. The concept of an annuity originated in the Roman Empire when particularly officers served the empire in combat and did military service. They were granted what was then called an annua, and that meant annually they would receive a payment from the empire. That made financial sense back in those days because the essential purpose of the Roman legion was to go out and sort of conquer new lands and make them become tax-paying members of the Roman Empire. So having the military sort of get a share of that excess money that was coming in based on their exploits was reasonable. The current use of the term annuity is almost always given in that same kind of sense. It's like retirement money. If you get an annuity, it means that you paid somehow in advance. Now, not necessarily by military service, but often by actually investing money. But that after you've made that investment into the fund, it's going to pay you annually an income. And in that guise, this is something that becomes an insurance product. A lot of insurance companies will run annuities. The reason is the amount of money that gets paid back to the person depends on how long they live. And it's different for different people, obviously. So the insurance companies spend rather a lot of effort on trying to figure out how long people live. And so what would be the reasonable amount of money to repay their investment with in the annuity. What we're actually looking at is not that sense of an annuity, but really we're describing the sinking funds version of things. If you've heard the idea of a corporation floating a bond in order to make some capital payment, that's the idea of a sinking fund. Is it's the antonym of a floating. So floating a bond is getting money from the public to buy some piece of equipment or make an investment into your business. Sinking that money, or the sinking fund idea, is to pay the bond back. So that's how the public gets paid off, and of course you pay them off with interest. So let me jump into the formula for this sucker. It's not pretty. Here it is in the textbook. I've actually also written it out on a piece of paper, but just look at that thing. M and then 1 plus r over n to the nt minus 1, then the whole thing divided by r over n. It looks heinous to begin with. You look at that and think, oh, God. So we're going to take that apart in pieces and see that actually it's not all that bad. It's really just combining two things that we've already looked at. So let me switch to this view. Excuse me, it took a little second to find it. So what we're talking about is called the future value of the annuity. What is the setup for an annuity? And this is often the case for people making retirement savings into an annuity fund. You pay a particular monthly payment over a long span of time, and every month, you're putting money into it. Now, clearly, when you get done, you're owed some interest as well. But you've got to think about this. The very last payment you put in, it only sat in that fund for a month before they began, the other phase of the annuity is they begin paying the money back to you. If it's only been in there for a month, it hasn't accrued very much interest. On the other hand, the very first payment you made, that first monthly payment, it would have required a lot of interest. So we're going to see how that future value formula comes about. I'll just mention here that it's also known as the accumulated value, probably the reason the letter A gets so often used for it. So this is the basic setup, not a Roman Legion's annuity, but a modern sinking fund annuity. You've got a fixed payment, M, and that is added into the fund or into an account n times per year. Now, money that's in the account accrues interest, and there's an annual rate, R%. Oh, actually, I've sort of misspoken there. It's not R%, it's R. The percentage is often what we say, but we reinterpret that as a decimal. So really, I should recross that off. Say R as a decimal. Well, so if you mean 5%, that means the R would be 0.05, okay? Okay, monthly payments are typical. That's very common. Quarterly isn't so strange, but monthly is reasonable. So M would be your monthly payment, and the N, the number of compoundings per year, or number of payments made per year, is 12. So that means the interest is computed with monthly compounding, and the payments are added on a monthly basis. Those things need to match. So here I've written down the kind of form, a crude outline form of what the accumulated value is going to look like. The very last month you put in a payment of M, and that didn't sit around long enough to accrue any interest. But the month before that, you put in your payment, and it accrued one interest payment. So this number Q here is actually one of the payments. Now that means Q is 1 plus R over N. Right? That's the multiplier that you hit an amount by in order to add on a month's worth of interest. If it was monthly, it would be 12. Right? So yeah, so this is the first month, this is the second month, the third month, the very last month. I don't know right now. I actually do know, but we haven't reached that point. I don't know how long we've been making the payments yet. But we'll fill in that thing. For right now, I'm just going to say it's K. Okay, so what we need to do is be able to figure out a sum like this, where we've got some number out front, and then a whole bunch of powers of Q. So I just very quickly have done something that maybe is fairly obvious to do. Each one of these terms had an M in it, so we can factor that out of all of them, and you end up with M times something that's just a powers of Q added together, with that one there being the 0th power. Actually, it might be nice to think that this one is 1, and that one is Q to the 0. Now, let's leave it as 1, because anything to the 0 is 1. Sorry. Bad to scratch something out when you mean to put it back. Well, so 1 plus Q squared on up to Q to a big power. Now, if we can figure out how to add up those things, then we'll just multiply by M, and we've got our guy. So I want to call that sum of the powers of Q something. Let's call it S. What's kind of cool is you can work out what that sum is by a little piece of trickery. What we're going to do is determine what Q times S would be, and then subtract to make a little bit of magic happen. All right, so I did that with the video paused. Might as well have written it out in a sense, because I need you to sort of analyze what I've done here. We multiplied the variable S, the sum of all these things, by Q. So where it was a 1, I got a Q. And where it was a Q, I got a Q squared. Q squared became Q cubed, and Q to the K became Q to the K plus 1. What's cool about those two things is if I take the latter one and subtract the former, if I do Q times S minus S, most of the stuff in between is going to cancel out. See how both of those things have a Q in them? They all have Q squareds in them. They all have, well, both of them have Q, well, depending on what K is. But generally, you're going to have a whole lot of cancelings, including Q to the K is going to have, right back here, it's going to have Q to the K in the other sum. So that'll get canceled. So the two things that survive are Q to the K plus 1, which is counted with a plus sign in this difference, and 1, which is being subtracted, so that's a minus. In other words, this is called telescoping. The sum just collapses. Q to the K plus 1 minus 1. Now, okay, let me rewrite what I just had on the previous slide. Qs minus s is equal to q to the k plus 1 minus 1. The point we're after all, we wanted to solve for s, right? We want to know what that sum of the powers of q was, and that starts to become doable now. Look at the algebra here. You could factor an s out of both sides of that difference there, and you have s times q minus 1. I haven't done anything to the right-hand side, so that remains as q to the k plus 1 minus 1. And I hope you all see what we do next is just divide off that q minus 1. So s ends up being q to the k plus 1 minus 1 divided by q minus 1. All right. So now that is actually a standard thing. That's called the sum formula for a geometric series. And that is referred to in the textbook, like it's something you're supposed to have seen before. And I'm not sure if you have. So I wanted to make sure that we all saw this derivation of what the sum of a geometric series is like. Well, what is the q and what is the k, the upper limit of the sum? Yeah, in our scenario, the value of q is essentially a month's worth of interest, or it's the multiplier you use to do a month's worth of interest, except it might not be monthly. So it's n is the number of compoundings per year. Q then is 1 plus r over n. Let's say what k is too. In the scenario we're after, you've done n compoundings per year and n payments per year for a bunch of years. Usually that would be t because it's time, right? So the time variable is what you use for the number of years that have transpired. But this interest rate or this interest multiplier is happening n times per year. So our k is actually n times the amount of time that's elapsed. Well, now we're in a position to put that all together to see where the formula for the accumulated value of an annuity comes from. Well, that's interesting. When I wrote this down, I realized that I'd lied to you slightly. So I'll explain what the lie is. But in any case, we're still looking at the formula where we have the last payment that's not accrued any interest. The next to the last payment got 1 month's worth of interest. Then the one that got 2 months worth of interest, 3 months worth of interest, and finally this many months worth of interest. The problem is that exponent is wrong. It's off by 1. And you should, well, here's a quick way to see that. The m that's up front in here, you might think of that as being multiplied by 1 plus r over n to the 0 power. That makes sense because this term had a 1th power, 1st power, 2nd power, 3rd power. But if there were actually nt payments, the number of compoundings times the number of years, we're off by 1 in that because 1 through nt would be nt, and we've got also a 0. What we really have in that power is nt minus 1. So the product of the number of compoundings and the number of years actually gives you 1 more than the amount of interest payments, or the amount of interest payments that the payment that's been in the account the longest would get. 1 plus that minus 1. By the way, there is another version of this that's called an annuity due, an annuity DUE. And like the previous version of things, this sum has an m in every single term, to NT, so I'm going to just pull that then out. The first term is eliminated. You wouldn't have that. And then what's remains, actually, I guess I should, they're basically the same thing with a shift happening. The question is, do you make the payment at the end of the month or at the beginning of the month? This is the version for it at the beginning of the month. Yeah, let me all right, so yeah, that's the formula, or that's the sum that we're going to try to get after. Well, but first just off, a second ago, I said that let's figure out what's in the geometric series. You have 1 plus r over n to the q, right? K plus 1. But then you're subtracting 1 from it. You see how you're just going to get r over n then there over q minus 1. And we had that Q was our 1 plus R over N. The A we're after looks like something that's got an M in every single term. So let's just pull those M's out, all of them out, make it one M out front. And what remains inside is 1 plus R over N plus 1 plus R over N to the second power. That was the first power. This is really the 0th power. And it goes on until we get to n times t minus 1. Let's put the dot dot dots right here. Okay, so that's m times something we know from this sum of a geometric series formula. That's equal to m times, let me say it in terms of q first. Q to the k plus 1 minus 1 over q minus 1. But what q is 1 plus r over n. Great, so this is, again, the bottom is going to end up with just having r over n in it. Because we're adding 1, but then we're subtracting 1. The top has our q, 1 plus r over n, to a power that's 1 greater. Remember this had k plus 1 in it? 1 greater than what the exponent is there. That's kind of cool because that subtracting 1 made this turn out to just be nt. And then we're subtracting 1 from that, and I've dropped the m, silly me. There's supposed to be an m out front of that thing. Do you want to compare that to what we started with? Let's see if I can put them on the screen at the same time. The only difference here is that I put square braces around the junk in the top of that and lifted this m up into the numerator of the fraction. But that's still allowed because m is the same as m over 1, and that's how you would work with fractions. So this is indeed the formula that we looked at in the beginning that seemed so hairy. Yeah, so that's our future value for an annuity. Now, often annuities have this kind of feature where we see money being paid into them over a set period of time, and then they have that other phase where the money is coming out repaid to the investor. The way they talk about this in the book is almost always in the sinking a bond kind of vein, where that repayment part is ignored. So there's a rising portion where the balance of the annuity is rising, and then there's a descending portion. We're just not worrying about the descending portion. By the way, if you find yourself working in the finance world, there are about 20 or 30 different ways that annuities can be structured. So yeah, you have to be pretty careful about what's the particular details of the annuity thing that you're actually calculating. So this is an example of it, essentially the simplest kind. All right, well, that's the end of it for today. I hope you have a good rest of your day.